In this screencast, we're going to learn how to find the equilibrium concentrations for an equilibrium reaction given the constant and some starting conditions. We should start out by reading the problem. The problem says a 1 liter flask has 1 mole of H2, 2 moles of I2 at 448 degrees Celsius, and the K for concentration, the Kc, is 50.5 for the H2 plus I2 yields 2HI reaction. And it wants to know what are the concentrations of the substances at equilibrium. So the information that they've given us is that we have 1 mole of H2, 2 moles of I2, and we have a K value. So we've plugged that into our ice chart, and we know that we don't have any information about how much the change is going to be or what we're making at equilibrium. But we can see that our ratios, our coefficients are 1, 1, and 2. So we know that if we change H2 by a factor of X and I2 by a factor of X, that we will be changing our HI by a factor of 2X. And we know that these are going to be reduced and this is going to be formed. So we have 2X is our equilibrium value, 1 minus X. Forgive me for dropping the zeros. I don't have enough space. 2 minus X. And we know that K, which is 50.5, is going to be equal to products over reactants. So 2X, the whole thing squared, over 1 minus X. Sorry, the pen is not cooperating. There we go. 1 minus X times the 2 minus X. And so now we can solve for X. There's a couple of things that I notice when students are doing these problems. They don't always do the algebra correctly. They drop terms. They got to be careful. You need to be careful. 2x, the whole thing squared, is 4x squared. And it's going to be over, this is a FOIL problem. So 2, and I'm going to put those zeros back in now that I have space for them. So 2 minus 3.00x plus x squared, and the whole thing equals 50.5. All right. You might be recognizing something here. We can simplify this to have 4x squared equals, we're going to factor, this is really nothing more than just a whole bunch of algebra. And you do need to be careful that you do your algebra carefully. And you don't lose or change signs or anything else. So when you factor that out, and if you were following along, you can start to see something like a quadratic forming. So if you factor in the 50.5 to this parentheses here, and then you set it up so that you have 0 equals, because that's what you need for the quadratic, you will have 101.0 minus 151.5x plus 46.5x squared. So here's the thing. Sometimes you can make an assumption. And you can make an assumption when your K value and your change values, or your equilibrium values, are more than, we're going to go 3 to 4 decimals apart. Okay, 3 to 4 decimals. Wow, that's not writing very well. Let's try that up. We're going to write it down here. 3 to 4 decimals difference. So if our K value had been like 550,000, we could make this assumption because 550,000 would be much more different than our factor that we're subtracting here. If it had been if our K value had been like itty bitty, we would be okay as well. Why would we want to make an assumption? Well, if we can make the assumption that the change attributed to this is so negligible we're so much smaller than the 1 and the 2, then we would not have to worry about those additional x values in our equation, and we would be able to solve this problem with a square root. But because our k and our values are very similar, we cannot make the assumption, and we have to process through this quadratic formula. So if you're still following along, you have a quadratic equation, which you guys remember from math, is minus b plus or minus square root of b squared minus 4ac, the whole thing over 2a. And if you look at the equation that we have 0 equals 46.5 x squared, and you have a negative 151.5x and a 101.0, and those values match with our A, B, and C. So we're going to plug that in and do the math. And I'm pretty confident that you can plug these numbers in where they belong and do the math. It sometimes takes more than one time through. I'm not going to show it here, but you can plug them in and do the math. You should be able to get that x will equal 2.323, or it will equal 0.935. Because remember, we have that plus or minus up here above the fraction line. So why can't both of these numbers work? Well, what you need to do is you need to substitute these x values in up here in your E line, in your equilibrium line. You need to substitute these values in, and you cannot make a negative amount of a concentration. So if you plug in 2.323 in for x, you get a negative value for both of them. So that value does not work. So we can discount it right away because it will give us a negative number. What we can do is then we're going to take, well, that would not make sense. Hold on a second. There we go. We're going to discount just the one value. We can take this value and plug it in for x in all three places and solve for our equilibrium concentrations. So our concentration of H2 is 1.0 minus the 0.935, and that's going to get us a value of 0.065. When we plug our 0.935 into the I value, our concentration of I2 would get 1.065 molar. This is molar also. And our concentration of HI would get a value of 1.87 molar. So that's how you do the problem the long way. There is a shorter way. Like I said, there's the assumption, and I'll talk about that next. All right, so let's talk about these assumptions. The assumption can be made and holds true when the decimals of the K value and the equilibrium concentration values before the X are more than 3 digits different. For instance, if you had a 1 or a 3.1 times 10 to the negative 7 equilibrium constant, and your concentration values are in the neighborhood of 0.1 or even 0.01, we would know that if we were subtracting x, if we were to take minus x off of this value, and x is a value based on this k, this times 10 to the negative 7, that x would be so small that it would not effectively change the overall concentration of the equilibrium value, and therefore we can dismiss it as being not negligible. It's not negligible. It's negligible. So we can dismiss the x in that case. Okay, and it no longer is part of the calculation. So then we would only have something, say for instance, we might have 4x squared equals some value that you can then square root to move on and find an answer. There are lots of examples that we'll be doing in class and in the textbook. I'll show you some of those in class.